Okay, this is Math 105, section 4.3. Now we're going to talk about logarithmic functions. Okay, so remember our exponential function, a to the x with a greater than 0, okay? And we say a is not equal to 1, of course. We know that that function's 1 to 1 by the horizontal line test, okay? This is for a greater than 1, but you can see that, this function, which goes, remember, goes through 0, 1, right? That it's, well, our domain and range, our domain is all reals and our range is y is greater than 0, but as we draw horizontal lines, this thing, we can only cross it once, right? In fact, or not at all. So we can't cross it more than once. So it is a one-to-one function, which means it does have an inverse. But the inverse is kind of tricky to find explicitly. In fact, we can't find it explicitly. So we're going to develop this new function that's the inverse of an exponential function. We're going to call it a logarithmic function. Okay. So the idea is this. We take y equals a to the x, and we switch x and y, right? So now we have x equals a to the y, but we can't get y by itself here. That's not something we can do algebraically. So what we do is we develop this new function, and we call it y equals logarithm, base a. Now the base goes down below as a subscript instead of a superscript like we normally do for exponents of x, okay? So these two functions, this is the inverse function, and this one are the same, okay? So when you see log base y equals log base a of x, we can kind of do this thing. We can start here on the base, because that's the base, and this is the base, and we go over across the equal sign to go to the y, so a to the y, and then cross equals again equals x, okay? So these mean the same thing. A to the y equals x, or x equals a to the y, is y equals log base a of x, okay? So we developed this logarithmic function to get y by itself. See, this is not explicitly defined as the inverse function because we don't have y by itself. Here it is, okay? So, you can translate your log function by going base, starting with the subscript, cross the tracks, these would be the tracks, once, so a to the y equals x. Okay, so let me just write that in this kind of, so I have some room to show that, okay? So I'm going to use red here, but a to the, that's going to be to the power, and then equals, cross again, you see. So we have a to the y equals x. So that's how we can translate that to get it into an exponential function, an exponential form instead of log form. Okay, so that inverse function, f inverse, is called the logarithmic function, okay, with base a, and we call it log base a, okay. So we can say y equals log base a of x, which is the same as saying x equals a to the y, as I showed how we do that translation, okay. A is a positive number, a is not equal to 1, because remember that's our base, okay. So this is the logarithmic function with base a, log base a, okay. And we can think of log base a of x as the exponent to which the base a must be raised to give x. Okay, so we're doing exponent backwards, right? That's what an inverse function is, right? So you think of these two are the same, right? Log base a of x equals y means a to the y equals x. Or we can, remember, we start at a, cross the tracks, a to the y, and then cross again, equals x. Okay, so the logarithmic form is log base a of x equals y, and the exponential form of the same thing is a to the y equals x. Okay, base is the same, right? So we have the same base of a. Okay, so this is the log form, and this is the exponential form, but they're the same function. Okay, so if we have log base 10 of 100,000 equals 5, we can say 10 to the 5 equals 100,000. I'm doing that little thing where I start at the base and I cross the tracks twice. So 10 to the 5 equals 100,000. Okay. 2 to the third equals 8. Okay. 2 to the minus 3 equals 1/8. Okay. And then 5 to the r equals s. Okay. I'm just using kind of a general example there. Okay. So it's important that we understand that log base a of x is an exponent. Okay. It's just that it's a backwards exponent, right? In other words, log base 10 of 1,000 equals 3 because 10 to the third equals 1,000, right? Log base 2 of 32 equals 5 because 2 to the fifth equals 32. I'm crossing the tracks twice, starting with the base. So 10 to the minus, log base 10 of 0.1, 10 to the minus 1 equals 0.1. Okay. Remember, 10 to the minus 1 is 1/10, right? It's not negative. Okay. And then log base 16 of 4 is 1/2. 16 to the 1/2 is 4. Remember, that's square root, right? Okay. Remember when we take a function of its inverse, we get back to where we started, okay? So if we start with x and go a to the x, and then we take log base a of a to the x, we're undoing that exponent, so we end up back where we started, which is x. See, those undo each other. Now here we can say x can be any real number, right? Okay. And then we could start with log first. If we take log base a of x, this one isn't as obvious, but if we take log base a of first and log base a of x first and then take a to that power, we're undoing that log, so we get back to x. Now here we have to say x is positive because when you take a logarithm, you can only take a log of a positive. You can't take a log of a negative. So here x has to be positive. And we'll look at that when we see the graph. Okay, so here's our basic properties of logs. Let me make this a little bit tighter there. Okay. So first of all, we have log base a of 1 is 0. So anytime we have a log of 1, we have 0. Okay. Doesn't matter what your base is. Log of 1 is always 0. Log base a of a is 1. A to the 1 power is 1, is a, right? Log base a of a to the x is x. That's what we have up here. You know, that's this first thing we have here, right? We're taking a to the x and we're taking log base a of that. We're undoing that a to the x. So we get back to where we started. Okay. And then finally is the other one. A to the log base a of x equals x. And that one we have to think about a little more. Okay. So if we start with, it's the same thing we have up here, right? We start with log base a of x, start with x and take log base a. Then we take a to that power, we're undoing that log, and so we get back to x. So that's our fourth property of our logs there. Okay, so let's look at some numerical examples. Log base 5 of 1 equals 0. 5 to the 0 equals 1. You could say 5 to what power gives me 1. All right. Log base 5 of 5 is 1. That's property 1, by the way. Log base 5 of 5 is 1, so 5 to the 1 power equals 5. That's property 2. Log base 5 of 5 to the 8th power, we can say 5 to the 8th power equals 5 to the 8th, right? So that undoes the 5 to the 8th, that log base 5. You could say, think of it that way, and we get back to 8. So that's property 2. Okay. And then for property 4, we have 5 to the log base 5 of 12 power. Now this undoes the log when you take 5 to that power, so we're going to get 12 to finish. Okay. And this one, you know, it's not quite as obvious, but we're doing the log first, and then we're taking 5 to that power, same base here, and it undoes that log. So we end up with 12 where we started. Okay, let's talk about the graph of the log function. Okay, remember a one-to-one function has domain A and range B, then its inverse function, f inverse, has domain B and range A. Remember, we're switching x and y. Okay. So remember our exponential function, a to the x, a is not equal to 1, has domain all reals and range greater than 0, right? So its inverse function, which is the log base a of x, has domain x greater than 0 and range all reals. Okay. And remember when we graph an inverse function, so the graph of f inverse is obtained by reflecting the graph of the exponential function across the line y equals x. Okay. You remember we reflect the line y equals x for the inverse function, okay, which is that line that goes through halfway through the first quadrant, halfway through the third quadrant. It's a diagonal, cuts it in half. So we reflect across that line to get the graph of the inverse. And that gives us this. So here our blue is the a to the x. Okay, it goes through 0, 0, 1, right? And then here's our line y equals x is the yellow. Okay, and we reflect across that, we're going to get our log function, which is the red here. Now this goes through 1, 0. You see the reflection there, right? Across that line y equals x. Okay. Notice I can't have inputs that are negative or 0. I can only have my domain here. Let's write the domain out so we remember it. Okay. So for the exponential function, my domain is x can be anything, right? Okay. and my range is y has to be positive. For the log function, just the opposite, right? My domain says x has to be positive, so I can't take a log of a negative or a 0. Okay. And my range is y can be any real. Okay. And we can see that as we look at the graph, as we look at the red graph, right? It's x doesn't start for x until x is positive, and then it goes y, it goes way down here, and it keeps going up slowly. Now notice when as I get close to 0 for x positively, my log is very large negative, but it grows really fast until I get to 1, 0. And then after x is greater than 1, it grows really slowly. Right? So a log function grows really slowly when x is bigger than 1, grows super fast when x is between 0 and 1. We can kind of compare that to a to the x. The fact that y equals a to the x is a very rapidly increasing function for x greater than 0 when we're saying a is greater than 1. That implies that log of x, log base a of x, is very slowly increasing for x is greater than 1. Okay. And since log base a of 1 is 0, the x-intercept of the function, the log function, is always 1. Okay. And the y-axis is a vertical asymptote. Okay. Because log base a of x approaches minus infinity as x approaches 0 from the positive side. That's what that little plus means. This means where x approaches 0 from the right-hand side. So we can't approach from the left-hand side because it's undefined there. So we're kind of going this way and looking at x approaches 0, and we can see our x goes way down. And we saw that from the graph on the previous slide. Okay, so let's look at how we graph this using a table of values. Okay, so we're going to use log base 2 of x. And when x, now what we can do is we can look at, x being 2 to the third, right? We can look at powers of 2, and that kind of helps us get our numbers, okay? Like if we look at 2 to the third, the log base 2 of that is just 3. We just take the exponent out. Okay. We look at 2 squared for x, the log base 2 of that is just 2. If we look at 2 to the 1, the log base 2 of that is just 1. 1 would be 2 to the 0, which means that we would get 2, 0 for log base 2 of x. Okay. 2 to the minus 1, which is 1/2, we get minus 1. Okay. 2 to the minus 2 for x, which is 1/4, we get minus 2. 2 to the minus 3 for x, which is 1/8, gives us a minus 3 for the log. And then finally 2 to the minus 4, which is 1/16, gives us, for x, gives us minus 4 for the log. Okay, so you can see as we have 1, 0, right? Okay, there's point, okay. And then 2 to the 1 gives us 1, right? 2 to the 2 gives us 2. 2 to the 3 gives us 3, right? See, if we're kind of doing it strategically. We're saying, let's take our base to certain integer powers, and then taking the log is easy because we just take the exponent out, okay. And then 2 to the minus 1 would be 1/2, so 1/2 we're at minus 1, okay. And then at 1/4 we're at minus 2, 1/4 for x. 1/8 we're at minus 3, and 1/16 we're at minus 4. We can see it's going way down. It never hits the y-axis, okay. So however small you make x, positively, it's always going to be something where you're not going to, you can't use 0, right, for x. So it's got to be greater than 0, and you're just going to get lower and lower. Okay. So we do have that vertical asymptote of the y-axis. Okay, let's compare like how the logs, at different bases go. Okay, so notice they all go through 1, 0. Okay, all the logs go through 1, 0. Log base 2 grows the fastest. It's still slow growth, but it's the fastest. Then log base 3 is below that. Okay. Now, as we go to the left of 1, we look at fractional values of x, they switch roles. So now the red is decreasing much faster. Okay. And then the black doesn't decrease as fast. Okay. Now let's look at the blue. That's log base 5. See, it doesn't grow quite as fast, right? And then it doesn't decrease quite as fast either. Or actually, it doesn't decrease quite as fast. Okay. And then log base 10 of x grows the slowest of those four, okay, and then it decreases the slowest. Okay. But they all meet at 1, 0. Okay, so it's kind of like, it's actually a reflection of 2 to the x and 3 to the x and 5 to the x and 10 to the x, right? If we look at those, they're going to be up here. Okay, and they would just be a reflection of those across the line y equals x. So we'll look at that graph in class too, just to verify that. We'll look at this family, compare it to the 2 to the x, 3 to the x, 5 to the x, and 10 to the x. So as I said, these graphs are drawn by reflecting the graphs of 2 to the x, 3 to the x, 5 to the x, and 10 to the x across the line y equals x. Okay, let's look at a couple examples where we're translating or shifting these graphs. So let's sketch the graph of g of x equals minus log base 2 of x. Okay, so we start with log base 2 of x, which is the blue here, right, which we've just looked at. Okay, and what we're doing is we're changing y to the opposite. See, my y starts at log base 2 of x, and now we change to negative. So remember, when you change your y, you're reflecting across the x-axis. So we take the blue, reflect it across the x, we get the red. Okay, you reflect this part, you get that. You reflect this part, you get that. Okay, so minus log base 2 of x would be the red one here. Okay, now we're looking at h of x equals log base 2 of minus x. Okay, so here's our log base 2 of x that we start with. Okay, and now what we're doing is we're changing x to the opposite, right? Which means we reflect across the y-axis. Okay, so the blue becomes the red here for log base 2 of minus x. So again, it's just recognizing what we're changing, right? In the previous one, we were changing our y to the opposite. Here we're changing our x to the opposite, so we're going to reflect across the y-axis. Okay, when you don't see a base, we're assuming that that's base 10, and we call that our common logarithm. Okay, so our common logarithm will, if you see log base 10 of x and you see it without the base, that just means log base 10 of x. Okay, so log of 10 is 1 because log base 10 of 10 is 1. Okay, log of 100 is 2 because log base 10 of 100 is 2. So we don't, if we don't write the base, we assume it's 10. Okay. Okay. How do we find log of 50? Okay. So you can think of it this way. Log base 10 of 50 and call it, y or something like that. Okay. Here we're. So what we're doing there is we're translating, right? So we're taking 10 to the y equals 50, okay? So we need to find the exponent y such that 10 to the y equals 50. So that's how we get that translation there. Now we could say, we could approximate because log of 10 is 1 and log of 100 is 2. So log of 50 is going to be between 1 and 2, okay? So, we couldn't really use a linear approximation. I mean, we could sort of in saying, well, it's probably closer to 1 than it is to 2, but not much. Okay, but we have usually, for something like this, we would use our log function or scientific calculator. So I wouldn't ask you to calculate this log by hand. Okay, but we can, estimate that it's between 1 and 2 because we know log of 10 is here and log of 100 is here. We're talking about log base 10, right? Because it's implied there. Okay, let's look at some applications of logs. One thing we use logs for is where something where we look at the measurement of something and it's kind of compressed. Okay, in other words, the perception of our loudness when we hear a sound, we use decibels, right? But the physical intensity of a sound can vary very widely. Okay, so what we do is we take that physical intensity, okay, we call it I, and we divide it by I0, which is a physical intensity of a barely audible sound. Think about the quietest whisper. And we take a ratio of those things. Okay, so we can say, let's say this thing is 10 times as loud as this, right? Like the sound that we're hearing is 10 times as loud as a whisper. Okay, well, we take the log of that, base 10, we're just going to get a 1 here. Okay, if the sound we hear is 100 times a whisper, then we're taking log base 10 of 100, which is 2. Okay? If the sound we hear is 1,000 times the intensity of a whisper, then we're going to take a log of 1,000, which gives us a 3. Do you see every time that our physical intensity that we hear, of the sound we're hearing, goes up by a factor of 10, by times 10, not plus 10, but times 10, this thing only goes up by 1. Okay? And then this 10 in front actually is going to make it go up by 10. Okay? So what happens is that as x goes times 10, y, now it would normally go plus 1 because of the log here, okay? But because we're multiplying by 10, it's going to go plus 10, okay? So this is kind of what's happening here, that every time x being our input, this would be our input, would be the I, kind of the I. Let's put this, let me say what that is. Okay, so I would be the x, okay? And then, let's not do it that way. Let's call I, and this would be our B, would be our Y, okay? So basically that every time the intensity of our sound goes up by a factor of 10, then our perception, the decibels, goes up plus 10, okay? So this goes from 10 to 100. This would go from 10 to 20, okay? So, you know, it's a big jump in the X in the input, and it's plus 10, you know, times 10 in the input, and just plus 10 in the Y, okay? All right, so that's how we model our decibel scale, okay? So there's our decibel scale. It is 10 times a log of I over I0. Remember, where I0 is kind of like our initial sound that we can detect. It's sort of a whisper, okay? So let's find the decibel level of a sound, loudness of a sound whose physical intensity is 100 times that of I0, okay? So we can say that I equals 100 times I0. In other words, this I over I0 will be 100. Okay, so here's the sound that we're hearing, which is 100 times a little whisper. So this is going to be 100. So we're taking 10 times the log of 100, which is 10 times 2. Let's put a little times there, because that should be 10 times 2, not just 10. Okay, and we get 20. Okay. So if your sound is 100 times a whisper, your decibel scale is going to be 20 dB. Okay. So it's you think about that. It went 100 times, then go up plus 100, but times 100. 100 times a whisper, and your scale, the loudness is 20 dB. Okay. Okay, kind of the most important log that we'll be using, and it's actually one of the most convenient, is the number E base. Okay, and we call that our natural logarithm. Okay, we actually don't use base 10 that much, even though we could call that our common log. And when we say log, we're referring to log base 10. But our natural log, we actually use a little bit more, base E. Okay, so logarithm with base E is called the natural logarithm, and we just call that's log base E of x, and we just give it a shortcut. We call it ln of x. So anytime you see ln of x, it means log base E of x. And we usually write ln of x instead. Okay. And as we know from before, y equals ln of x is the inverse function of the natural exponential function y equals e to the x. Okay? Just like, y equals log base 2 of x is the inverse function of y equals 2 to the x. Okay, so now we're using base e instead of base 2 or 3 or 5 or 10. Okay, so this is log base e, okay, and the inverse of y equals e to the x. Okay, so here's our graph of y equals e to the x. Remember, it's between 2 to the x and 3 to the x, right? And then if we reflect that across the line y equals x, we get the red, which is y equals ln of x. Same domain and range as our log base 2 and log base 3 and log base 5, etc. Okay? And then this is, the equivalency, right? So ln of x equals y is the same as e to the y equals x. And remember, we can do that by crossing the tracks. So here, remember, this is log base e, so we go e to the y equals x. This is, remember, ln of x is log base e, so we have base e to the y equals x. So that's how we get the same, the equivalent there, exponential equivalent of that. Okay, so the natural log properties have the same properties as the regular logs, log base a. So ln of 1 equals 0, okay. ln of e equals 1. ln of e to the x equals x. We're undoing that natural log, that exponential function. And e to the ln of x equals x, we're undoing the natural log with e to that power. Okay, so kind of just using those same properties we looked at before, but specific to base e. Okay, so let's look at some numerical examples here. ln of e to the 8 equals 8. This undoes the e to the 8, and we take the natural log, or we can say 8 to the 8 e to the 8th power equals e to the 8. Okay. ln of e to the 1 over e squared is ln of e to the minus 2, so that just cancels out the e, which gives us a minus 2. And then ln of 5, here we would just use a calculator to approximate that. If you see ln function key on your calculator, that's taking the natural log. Okay. Okay, let's look at an example where we have this function, ln of 4 minus x squared, and we're taking the domain. Okay. Remember logs of any base, the input into a log has to be positive. So 4 minus x squared has to be greater than 0. Okay. So remember how we do that, right? We have to do our key numbers, right? So if we have 4 minus x squared is greater than 0, we've done this so many times before, right? But we factor, 2 minus x times 2 plus x. Difference of squares is greater than 0, so we have our key numbers of 2 and minus 2. Okay. And then we look at our intervals, right? Okay, so we go between 2 and minus 2. And then we look on the outsides, right? So we go here, here, and here, right? And we test the sign, okay? So if we tried minus 3 over here, we would get a negative, okay? If we tried 0 here, we get a positive. And if we did 3 over here, we get a negative. So we're looking for the part where it's positive, right? So it's going to be between minus 2 and plus 2. So there's our domain. Remember, it can't be equal to 0. This thing has to be greater than 0. Okay, so that gives us x squared minus 4, right? Okay, so we're looking at the positive here, right? 4 minus x squared is greater than 0. So our domain is between minus 2 and plus 2, not including the endpoints.